The size and mysteries of the universe have always amazed people. Black holes, which have gravitational pulls so strong that nothing, not even light, can get out, are one of the most interesting things about the universe. Up until recently, we only knew about black holes through theories and indirect observations. But the development of virtual reality VR technology has given us new ways to learn about these mysterious space objects. Scientists thought they could see black holes by taking pictures of their shadows against the light of their surroundings, but they still couldn't see something so far away. To take on the challenge, a group of people got together and set up a network of telescopes called the Event Horizon Telescope, or EHT. They set out to take a picture of a black hole by improving a method called Very Long Baseline Interferometry, VLBI, which can be used to take pictures of things far away. All kinds of telescopes are used to see things far away. The diameter, also called the aperture of a telescope, determines how much light it can gather and how well it can see small details. To see details in things that are far away and look small and dim from Earth, we need to gather as much light as possible with a very high resolution. To do this, we need a telescope with a large aperture. That's why the VLBI method was so important for getting a picture of a black hole. VLBI works by putting together a group of smaller telescopes that can be set to look at the same thing at the same time, making them act like one big virtual telescope. Some of these smaller telescopes are also made up of more than one telescope. This method has been used to track spacecraft and take pictures of radio sources in space that are far away, like quasars. The aperture of a giant virtual telescope, like the Event Horizon Telescope, is the same size as the distance between the two farthest telescope stations. For the EHT, the two farthest telescope stations are at the South Pole and in Spain, so the aperture is almost the same size as the diameter of Earth. Each telescope and the array focuses on the target, which is the black hole in this case, and collects data from where it is on Earth. This gives the EHT a piece of the full picture. The better the image resolution, the more telescopes are in the array and the farther apart they are. The Event Horizon Telescope team chose two different targets, each with its own challenges, to test VLBI for imaging a black hole and a number of computer algorithms for storing and synchronizing data. The team was interested in Sagittarius A because it is the supermassive black hole closest to Earth. It is at the center of our Milky Way galaxy, 26,000 light-years away, which is 156 quadrillion miles. In astronomy, a black hole is always marked with an asterisk. Even though it is not the only black hole in our galaxy, from Earth it looks like the biggest one. But because it is in the same galaxy as Earth, the team would have to look through pollution, like stars and dust, to see it. This would mean that there would be more data to filter out when processing the image. Still, the EHT team chose Sagittarius A as one of the two targets, because the black hole is interesting to people nearby and is fairly big. The supermassive black hole M87 was the second target. M87 is one of the biggest supermassive black holes that we know of. It is at the center of the huge elliptical galaxy M87, which is 53 million light-years away, and that is 318 quintillion miles. M87 has 6.5 billion solar masses, which is a lot more than Sagittarius A, which has 4 million solar masses. One solar mass is the same as the mass of our Sun, which is about 2 × 10 to the power of 30 kilograms. Scientists were interested in M87 not only because of its size, but also because, unlike Sagittarius A, it is an active black hole. Matter falls into it and comes out at jets of particles moving at speeds close to the speed of light. But because it was so far away, it was even harder to catch than Sagittarius A, which was close by. Katie Bauman, a computer scientist with the EHT who led the development of one of the algorithms used to store telescope data during the processing of the historic image, compared it to taking a picture of an orange on the moon. By 2017, 8 scientists from all over the world were working together on the EHT, and more have joined since then. Before the team could start collecting data, they had to find a time when the weather at each location was likely to be good for telescope viewing. In April 2017, the team tried to observe M87 when the weather was good. Of the 10 days they chose, only 4 were clear at all 8 sites. For the EHT, each telescope had to be in sync with the others to within a fraction of a millimeter. This was done by logging an atomic clock to a GPS time standard. Because of this level of accuracy, the EHT can see details about 4,000 times clearer than the Hubble Space Telescope. As each telescope got information about the target black hole, the information was digitized and a timestamp was put on a computer disk. After collecting information for 4 days all over the world, the team had a lot of information to sort through. The recorded media was then moved to a central location because the amount of data, about 5 petabytes, is bigger than what the internet can handle at the moment. At this central location, the data from all 8 sites were synchronized using the timestamps and then put together to make a composite set of images that showed the silhouette of AIM-87's event horizon, which had never been seen before. The team is also trying to make an image of Sagittarius A by putting together more information from the EHT. The data also show how black hole structures like the accretion disk, which feeds matter into the black hole, and plasma jets, which shoot out from its center, form and behave. Scientists have thought about how an accretion disk forms, but until now, they have never been able to directly test their ideas. Scientists are also interested in how some supermassive black holes send out huge jets of particles that move almost as fast as light. As more data is collected by the EHT and put together by computer algorithms, these and other questions will be answered. Keep an eye out for that and the next image of a black hole, which is expected to be our Milky Way's Sagittarius A. Scientists have made a virtual reality VR simulation of Sagittarius A, the black hole at the center of our galaxy, which makes it easier for people to understand what is going on. Scientists at Radboud University in the Netherlands and Goethe University in Germany used recent astrophysical models of Sagittarius A to make a series of images. These images were then put together to make a virtual reality simulation of the black hole that can be seen on most VR consoles. Our virtual reality simulation gives one of the most realistic views of the black hole's immediate surroundings, and it will help us learn more about how black holes work, said Jordi de Villar, corresponding author of the study published in the journal Computational Astrophysics and Cosmology. We'll never be able to get to a black hole in our lifetimes, but this kind of immersive visualization can help us learn more about these systems from where we are now, de Villar said. Researchers also think that the virtual reality simulation could help get more people interested in astrophysics, including kids. The visualizations we made have a lot of potential to reach a wide audience. We used them to teach kids about black holes and they really got something out of it, de Villar said. This suggests that immersive virtual reality visualizations are a great way to show our work to a wider audience, even when it involves very complicated systems like black holes, he said. We all have an idea of what a black hole is supposed to look like, but science has moved forward and we can now make much more accurate pictures. These new black holes look very different from what we are used to seeing. Heine Falk, a professor at Radboud University, said that these visualizations are just the beginning.